So I guess I should just begin. So Jugal is exactly correct. Today, the plan is I just want to start by giving some motivation for explain what this conjecture is and some of the ideas which go into the proof. And then next time I'll introduce sort of the main methods which go into it and hopefully even explain how the proof goes. Okay, so it goes like this. So throughout, we're going to have the setting is we have a local surjective map, surjective local, I should say, like this. And since it's surjective, there is one residue field, so I'll call that K. Should tell me if my handwriting is unreadable or anything like that, or if I'm mumbling.
You could write little bigger.
Okay,
yeah.
I will write larger then. Okay, and also throughout, the kernel of this map is going to be called I. Okay, so in this situation, I mod I squared, that is called the conormal module, or the conormal module of specifically. Even though the ideal I is certainly not an S module because it lives inside R, I mod I squared actually is a well-defined S module if you think about the multiplication. It's actually well-defined on that. So the conormal module is an S module.
Excuse me. Can you please enlarge this a bit for those who are watching on slightly smaller screen? I guess this might be a little small.
Okay, I'll go even bigger than this. Okay. So I mod I squared, that's the kernel module. I'll just start writing very large. Oops. Geometrically, what this means is, or at least geometrically, there's the conormal sheaf. It's the conormal sheaf of spec S inside spec R. So the name is coming from geometry because it's telling you something about the deformation theory of S inside spec R. It's sort of, this is what normal is coming from, the normal directions to spec S inside spec R. So it's something about the deformation theory of spec S inside here. Sorry, I got to remember to write large. But I won't really talk about it from the geometric perspective. I'll just focus on algebra. But that's where the name is coming from, at least. So the idea is that geometric or algebraic properties of this homomorphism are going to give us module theoretic properties of the conormal module. So for example, a nice geometric property for a homomorphism would be that phi is complete intersection. Which means, in this context, we have a surjective homomorphism. Sorry, if there are things happening in the chat, you should just shout at me because I probably won't be able to see them.
So, see, I think if you can keep the iPad on horizontal position and right, it may the screen this may be slightly bigger then.
All right, let's try that.
Yes. Yes.
Okay.
That should be all right, I suppose.
Okay. No, that's better.
Okay.
Okay. So the idea is that we want to translate properties of phi, like being a complete intersection, into module theoretic properties over here. And this side is supposed to be easier to understand because it's a linear problem now rather than some nonlinear problem. So being a complete intersection, in this case, it just means this ideal here is generated by a regular sequence. Okay, so in that context, there is a translation of what that means into the conormal module. It turns out that implies I mod I squared is free. And in fact, having chosen generators like this, it's free on these classes of these things. So it's a free S module on sort of on the generators for the ideal. So you can be very concrete about it. And then the question, the question with any such invariant is, can you actually go back? Can you deduce geometric properties of phi just from properties of this invariant? So can you go back? And the answer in this case is yes. This implication is reversible as long as you add an extra hypothesis. So the theorem of Brand in 1967 and Vasconcelos independently also in 1967. It says we need to add this assumption that assume phi has finite projective dimension. So what that means is it's a homomorphism from R to S. So to say that phi has finite projective dimension means that the S has finite projective dimension as an R module, because there is a map here making S into an R module. So whenever I say phi has finite projective dimension, which is pretty much going to be the hypothesis all throughout, that's what that means. And it says that having made that assumption, if the conormal module is free, then phi is complete intersection. So there is a converse to this. Let's put a box around that, see how that looks. Yeah. So maybe just as a remark, oops, I'm still on box drawing mode. This assumption here is really important. So the projective dimension of phi is finite is important. For example, if I were just to take S to be the residue field of R, so this map, if the map from R to S was just a map from R to its residue field, that would always have a free conormal module, because it would be a module over a field, and therefore it's automatically free. But the map from a local ring to its residue field is very rarely complete intersection. That's equivalent to having a regular local ring. So that would be a counterexample for non-regular rings. So is there space here? Let's try here. So Vasconcelos continued to think about this, and eventually in 1978, based on various evidences that he had accumulated, he made the following conjecture. So again, projective dimension of phi should be finite, just as a background assumption. And the conjecture says that if, not just that the conormal module is free, but we sort of drastically weaken that to say if the projective dimension of the conormal module is finite, then as well phi is complete intersection. So this is the main that I'll be talking about throughout these two talks. Sorry about the boxes. Let's see if I can try that. Okay, so it's worth saying more about this. So what this is really saying is that the projective dimension of the conormal module is either 0 or infinity. If you think about it, it's saying, okay, if it's any finite number, then it has to be complete intersection. And I've already told you that for complete intersections, the conormal module is free. So in fact, it would be 0 at projective dimension 0. So there's some kind of rigidity. It's actually a sort of rigidity statement. It's saying that most finite projective dimensions aren't allowed. There's this complete intersection case here, and there's this non-complete intersection case here, and there's this huge gap between them where nothing happens. There's just no rings come up in there. So there's this sort of big gap between complete intersections and non-complete intersections, which is actually, philosophically at least, there are a lot of theorems of this form that for some reason there's a huge gap between convenient sections and non-convenient sections. So from that perspective, this conjecture makes sense, but there's more to it than that. Vasconcelos had a lot of evidence for this, so I'm going to write down. I'll write down some of the progress that was made to this and some of the evidences that were given. So various people made progress on this. It's true when I also won't write down all the things, so I'm sorry if I miss anyone out, but I'll just write down a few highlights. So to start with, in this original paper, Vasconcelos in 1978 explained why it's true when the projective dimension of S as an R module is less than or equal to 2. And he gave various other cases in this original paper as like motivation for why this might be a true conjecture. So he had a lot of interesting cases of, like, say, small height and some additional hypotheses like Gorenstein and stuff like that. It's worth looking at. There's also an interesting result of Gullickson from 1969, which says it's true when the projective dimension of the conormal module is less than or equal to 1. So they look very similar, but this one here is just a kind of a background assumption on the homomorphism itself. It's just saying that the homomorphism has projective dimension no more than 2. So I don't know, it's just a sort of background regularity assumption maybe. Whereas this one is, for me, a bit more interesting because it's getting at this rigidity thing I was talking about. It's saying that, in fact, the projective dimension of the conormal module can never be 1, because if the projective dimension was 1, then according to this result of Gullickson, that would imply that you had a complete intersection, but that would actually mean the projective dimension of the conormal module has to be 0, because for complete intersections, the conormal module is a free module. So it's saying that 1 never happens. In other words, we don't get projective dimension 1, so it's getting more at this rigidity type thing. I should also say this obviously is quite a long time before this, so really the history of this is that Gullickson proved a result which can be interpreted in this term. It implies this, and Vasconcelos pointed this out in a paper later. So we could also add Vasconcelos' name to that. And then a similar story for this one, Aoyama and Masuoka in 1977, both independently proved that this conjecture is true if I is almost complete intersection, which means the minimal number of generators of I, while it may not be equal to the grade of I, so that would be saying you had a convenient section, it's at most 1 off, so it's the grade of I plus 1. It's at most 1 more than the grade. So that's what it means to have an almost convenient section, and it's true in that case. Again, this appeared the year before, so they wouldn't have phrased it in this term, but Vasconcelos pointed out, okay, they have this, they both have these papers which imply that this conjecture is true for almost convenient sections. So if it's almost convenient section and the conormal module has finite projective dimension, then in fact it's an actual convenient section. Here's another interesting one, Herzog in 1981. Proved it's true if I is in the linkage class of a complete intersection, i.e. Lychee. So this is just a nice class of ideals about which you can prove various things. I won't talk about this, but that's a particular case in which it was known. And then lastly, this is the one I want to talk most about. There's Avramov and Herzog in, jumping forward to 1994, proved that this is true for graded rings over a field of characteristic 0. and also in the case where R is a smooth. So they did it for R being a polynomial ring, some graded polynomial ring. What's noteworthy for, so firstly, it was like a major jump forward. It's like a lot of interesting cases. But for me, what's interesting about this is that they used methods, or at least ideas, from rational homotopy theory. Which is not to say that there was actual topology getting involved, just in rational homotopy theory, they've sort of developed a certain type of algebra, certain kinds of DG algebras and things they do with them, and it turns out those ideas were useful. Those same ways of playing with DG algebras could be used to prove this thing. And in fact, the same is true in this case. So let's say as does. So the next result also uses ideas from rational homotopy theory. This theorem. So the theorem, I'll write it just initial way. So Vasconcelos' conjecture is true in all cases, and that's what these lectures are about. I'm going to try to explain why it's true. Okay. Maybe I'll write that. So the goal for these talks is to explain some ideas from rational homotopy theory. I guess I'll call this RHT. And to, as detailed an extent as I can in these 2 hours, explain the proof. I'll definitely get the main things involved and give some proofs of the main parts. Maybe just as a quick remark about some joint work with Trikanthi is that it turns out these same methods, these same ideas which go into this, or you can kind of adapt them, maybe quite drastically adapt them to make them look a bit different, but similar ideas, let's say, can also be used to prove results about the vanishing of Andrew-Quillen cohomology. Oops. Cohomology. So what should I say about that? There's it just turns out you can phrase these arguments in such a way that one can even simultaneously give a proof in essentially exactly the same way of this conjecture of Vasconcelos and some conjectures of Quillen about and a conjecture of Quillen on the vanishing of Andrew-Quillen cohomology, which was proven already by Avramov in 1999. So I won't talk about this, but it's interesting that these same things actually can also be used to do things about Andrew-Quillen cohomology. And it's because there's a close connection between, if you know these things, there's a close connection between the cotangent complex and the conormal module. So, but anyway, that's just a side remark. I'll leave it mysterious. So here's another remark, which is less mysterious maybe. So this result, the Vasconcelos is true, in the context of graded algebras over a field of characteristic 0. So in their context, i.e. R is smooth, and graded over the field of characteristic 0. They had Avramov and Halperin. Sorry, Herzog. Sorry, that's rude of me. There's a result of Avramov and Halperin showing up later. Avramov and Herzog prove stronger results, stronger statements about the projective resolution of I mod I squared. So what this says is that, okay, going all the way back to here, if the kernel module, if you have a non-complete intersection ring, then the kernel module has to have an infinite projective resolution. But they prove not only that it has an infinite projective resolution, but that it has a kind of as big a projective resolution as it possibly could. So let me state that as a question, which is still open. So that's if phi is not a complete intersection, must the resolution of the kernel module have maximal growth? i.e., so measuring the growth of a resolution, there's various different ways to do that. So this is an ambiguous question. So one concrete way to say it is must the radius of convergence of the Poincare series of I mod I squared. So you take the generating series for its resolution and see the radius of convergence of that power series. Must that radius of convergence be equal to that of K? So the residue field K always has the largest resolution in a very concrete sense. In particular, the radius of convergence will be as small as possible. So one way of measuring the growth is by the radius of convergence. So is it true that the kernel module has the same radius of convergence as the residue field K? This is something that Avramov and Herzog prove in their context. So it would be interesting to know if this is always true. Okay, any questions up to now? I haven't been watching the chat, so I'm a bit worried.
There is no question right now.
Okay. So it's time for me to start explaining what I mean by ideas from rational homotopy theory.
There's a question from Anjan Gupta.
Yeah, so that's a good point. Once again, yeah, so there would be, if you don't have that assumption, or at least some assumption on the homomorphism, then it's definitely going to be false, because you could take the map to the residue field would be a counterexample. So yeah, I should add this. Always the homomorphism is going to have finite projective dimension, and I'll try to remember to write that in various points. Okay, so rational homotopy theory. So here's just a sort of unreasonably rapid history of, at least from reading the history books as far as I know how it went. In the late 70s, two mathematicians, two commutative algebraists, Roos and Avramov, started to exploit methods from rational homotopy theory. Basically using DG algebras and the kind of things that they were using to prove things in local commutative algebra. And as time went on, they started to realize that there was more than just a superficial connection. There was actually kind of, they realized the connection, let's just say, let's be mysterious, it kind of ran deep. So there's like real interesting structural similarities between what happens in local commutative algebra and what happens in rational homotopy theory. So to be more concrete, Roos was interested, in the following question of Serre and Kaplansky. So in algebra, there was this question about must the Poincare series of a local ring, so that would be the sum over TTI times the ith-Betti number, the dimension over K of Tor I KK. So must the Poincare series of a local ring be a rational function, like a quotient of two polynomials in T. So for all local ring R with residue field K. And in topology, there was a similar question of Kabansky. If you start with a base space X, you can ask the following question. You can write down the following Poincare series for a space, which might look a bit strange, but the sum over TTI of the dimension of this rational vector space, the ith homology group of the loop space of X with rational coefficients. So must this be a rational function? And so like we have here, a kind of Noetherian, all the local rings are definitely Noetherian. In this context, you need a finiteness assumption on X. So this would be for X equals a finite based CW complex. Where finite CW complex means some space which is built out of finitely many like disks and spheres and stuff. So anything with like a finite triangulation, like a manifold, is definitely something to which this question applies. And you could complain that I've just written down two Poincare series, and I've used similar notation for them, but why would you actually believe that these are two questions? It turns out this is not a superficial similarity. These two questions are actually structurally related. There's a kind of common framework in which these two questions are a special case of one question. So it is actually like there's a deep connection between these two things. And in fact, Roos exploited this. So Anik in 1980 said that the answer is no. No for spaces. So gave a counterexample, a relatively small space X such that this Poincare series is irrational. And Roos had already proven that for spaces like this, you could turn that into a counterexample. You could turn that into a local ring, which was a counterexample. So according to Roos, that implied the answer is no for rings as well. So it turns out there are local rings. In fact, there are lots of local rings whose Poincare series is irrational. These are called bad rings. Anyway, I'm getting aside from the point. I'm more interested in the way that Avramov got into rational homotopy theory. He was interested in an invariant called the Homotopy algebra. So the rest of this talk is going to be about the Homotopy algebra, and a lot of the next talk is going to be about the Homotopy algebra as well and how to construct it. So maybe I'll explain the topological side, topology, but I won't properly explain it. I'll just say there is comes from first is that if you have a X is say a simply connected based space, then one can build from that a Lie algebra by taking the loop space of X and then taking all of the homotopy groups of X. And it turns out that assembles into a graded Lie algebra over the integers. And it turns out it's essentially impossible to understand that. Even for a very simple space, it's incredibly complicated to work out what this is. So the idea of rational homotopy theory is that you take this Lie algebra of the integers and you just tensor with the rationals. And then it becomes a lot simpler because all the torsion goes away. And then there are, somehow this procedure of just tensoring with the rationals introduces new algebraic tools which can be used to understand these very concretely, and those algebraic tools turn out to apply in local commutative algebra as well. So it's a graded Lie algebra. So in a similar way to how you would construct that, you can construct in algebra if phi, once again, from R to S is a local homomorphism. one can build from this a graded Lie algebra, pi star of phi. So it's graded. It always starts in degree 1, and then goes 2, and so on. 1, 2, 3, 4. So there's never anything in degree 0. So it always starts like that. And it is a graded Lie algebra over the residue field K. Let me tell you, for people not familiar with Lie algebra, what this means. It means each piece pi I of phi of this big graded vector space is a finite dimensional K vector space over the residue field, and there is a bracket that goes from pi I and pi j to pi I plus j, so just like a graded ring, which is written with bracket notation, so uv goes to u bracket v, and it's bilinear, as you would expect, and it's anti-symmetric, which means that it might be starting to write too small. So if you switch the order of the two things in the bracket, you get minus 1 to the ij vu, and plus the Jacobi identity which goes like this. U bracket v bracket w is the same as u bracket v bracket w in this order, but it's not associative. You also have ij like this, v bracket u bracket w. So the Jacobi identity is sort of like a replacement for associativity. It satisfies some other thing instead. And I should say, in characteristic 2 and characteristic 3, you need to be slightly more careful about this definition of what a graded Lie algebra is, because a few things can go wrong with these things. You need to add some extra conditions, but those won't show up in the proof, so we can safely leave them out for this. But one can look up, for instance, in Avramov's book about infinite Fourier resolutions, talks about what a graded Lie algebra is in details. You can check. So anyway, construction of pi star of phi. It's quite involved, or at least the way I want to do it is quite involved, and pretty much every method is involved to some extent. So I'll just say it uses DG algebra stuff, DG algebra techniques, and I will explain it next talk. Maybe I'll start explaining it this talk. I have time. So I promise I will explain how to construct the homotopy algebra homomorphism. For now, I just want to motivate why this is an important thing, and so I'll explain. I'll give some examples to see what it looks like and explain some of the theorems that are known about it. So, for example, one of the early theorems that was proven using the homotopy algebra, which is supposed to be motivation for why it's an important thing, is it was used. Was, for example, used by Avramov to solve Grothendieck's localization problem. Which says that if R is a local complete intersection, then any localization of it at a prime RP is also a local complete intersection. So this was originally proven by Avramov using the homotopy algebra. It's thanks to this theorem. This is an important theorem because it's thanks to this that we even have a notion of locally convenient intersection. It even makes sense to talk about locally convenient intersections because of this result. Is there anything else in the chat? No. Okay, so here's another theorem about how you can use the homotopy algebra to tell whether you have a convenient section or not. It is a theorem of various authors. So Felix, Halperin, and Thomas, some rational homotopy theorists. That was in 1982, and also Halperin in 87, and also Avramov in 99. So this is a kind of omnibus theorem where I'm combining various things. Oops, I'm already at the end. So let's say phi is a local map of finite projective dimension, and I want to, for some reason, state this in a slightly more general form than I've been doing before. So I'll actually say finite flat dimension because you don't need to assume it's surjective for this part. That means essentially the same thing. So let's say you have a homomorphism of finite flat dimension. If phi is a complete intersection, then the homotopy algebra of phi, let's write it in shorthand, is only in degree 1 and 2. It just stops there. So there's a vector space in degree 1, vector space in degree 2, and then the rest of the homotopy algebra is equal to 0. If phi is not complete intersection, then in fact pi I of phi is never 0. At least for I greater than or equal to 2. The homotopy algebra just is always non-zero forever. It goes on forever. And in fact, the dimensions of these groups grow exponentially. So it's another one of these things about how there is a huge gap between convenient sections and non-convenient sections. For convenient sections, the homotopy algebra is very simple and easy to write down and easy to understand. And for non-convenient sections, it's extremely complicated. It just sort of blows up and becomes exponentially big. So it's hard to even talk. It's hard to compute examples. Okay. So I should say as well that these authors are rational homotopy theorists. So at the same time they proved a result about spaces. The corresponding fact for topological spaces is also true. The rational homotopy algebra of a topological space falls into two possibilities. Either you have an elliptic space, in which case the rational homotopy algebra stops at some point, or you have a hyperbolic space, in which case the rational homotopy algebra goes on forever and is very complicated. So the same dichotomy and the same strange gap, between convenient section and non-convenient section also shows up in rational homotopy theory about the gap between what are called elliptic and hyperbolic spaces. Anyway, so these numbers, whoops. Epsilon I of phi, which are these dimensions. These are called the deviations of phi. So maybe you've heard of these numbers before, because at least the first few of them, the first, second, third deviations, maybe are important invariants for various uses, and one can define them by other methods. So you may have already heard of the deviations, and these are important invariants by themselves, and they have interpretations in terms of the homotopy algebra. They're just exactly the size of the Lie algebra in each part. So how's time? Time's good. Maybe some quick examples. So if we look at this local ring, which is two variables modulo just x times y. So that is a hypersurface. It's definitely a complete intersection. So according to the previous theorem, it should have a nice simple homotopy algebra. I'll call that this map phi. Then the homotopy algebra of this map phi is it's in 2 degrees. So let's say it's in degrees 1 and 2. And here it's a 2-dimensional vector space on 2 generators. I'll call A and B. And in degree 2, it's 1-dimensional. It just has a single generator, C. And the bracket is, there's only one possible non-zero bracket here. And the bracket of A and B is equal to C. So it's quite simple to write down. Here's a more complicated example, which is not a convenient section. So if I take this homomorphism from the residue, from the coefficient field to just the same local ring, but modulo the entire maximum ideal squared, then pi star phi is a free Lie algebra. It's a free Lie algebra on two generators in degree 1, which means that you sort of freely start taking brackets in all possible orders. And because this is not a commutative object and not an associative object, taking brackets in all possible orders really does blow up, and this thing will grow exponentially. There's really algebras are very complicated objects. Maybe I should say here, there's some space. There's some space here. So the bracket from pi 1 cross pi 1 to pi 2. So because it's graded, there's always going to be a piece of the bracket which goes pi 1 cross pi 1 to pi 2. And Sheridan had a paper in 1967 which explained how to write down that. So you can be very explicit. That's why I know how to easily write down this bracket, because there's a theorem of Sheridan which explains how to do it just by looking at the relations and kind of dualizing them in some sense. Anyway, so that was just some motivation about the homotopy algebra. It's time to get back on track, and I'm going to tell you now exactly the way I'm going to use the homotopy algebra to prove the theorem. So it goes for another theorem of Avramov and Herzog now. So we're getting back on track. So first I need a definition, which says if you take an element of the homotopy algebra, then, whoops, there's a thing called the adjoint action of U. It's written add U. Add U is, it just means bracket with U. So it's this map that goes from pi star of phi to pi star of phi, which is just take something in brackets with U. So it's just, we have this bracketing map. U is called central if add U is 0. So if bracketing with U just is completely 0, that means I have a central element. And it kind of makes sense if you think of the bracket as commutator, which one can certainly think of it as. So it's just saying U sort of commutes with everything, so it's central. But more interesting, for me at least, is U is called radical if we weaken this to just saying that add U is nilpotent. So rather than bracketing with U being 0, bracketing with U is nilpotent. So if you take anything and bracket with U enough times, you get 0. So it's not central, but sort of becomes central if you apply it enough times. So here's a theorem of Avramov again, and Halperin from 1987. Once again, we always need this background assumption that phi has finite projective dimension. Oops. And it says if every element of pi 2 is radical, then phi is complete intersection. Okay. So I'll explain this more. Just a quick remark, though. One can give a kind of nice modern proof. The proof there is quite nice, but certainly a more modern and maybe more conceptual proof of this theorem using what's called cohomological support theory. Which is something invented by Avramov, once again. Sorry, my handwriting is. And Bookweitz in 2000, I think, about cohomological support theory for convenient section rings, and I should add some other names here. Also, Jorgensen pointed out how there's a similar convenient section, a similar cohomological support theory for even non-convenient section rings, and also Politz, who developed this cohomological support theory for non-convenient sections, and in particular used it to give a criterion for when a ring is a convenient section, which is very powerful. Turns out you can use it to prove lots of nice things about which rings have to be convenient sections, and one can use that cohomological support theory type thing to prove this result. Okay, so that's anyway. So I can finally start tying things together. The connection to the conormal module is the following. So locally nilpotent is enough as well. So I was a bit, you're right, I was a bit vague about what nilpotent is here, and it's because, so also I should say this is not the usual definition of radical. If you know Lie theory, there's maybe a more precise definition of what it means to have a radical element in a Lie algebra. But this happens to be a very special kind of Lie algebra. It's what's called a Lie algebra of finite depth, where the various notions of radical all line up. So in this case, being locally nilpotent, I think, is equivalent. Yeah, being locally nilpotent is equivalent to being actually nilpotent in this case. In any case, okay, so the connection to the conormal module is this proposition, which may look mysterious now, but once I explain how to construct a homotopy algebra on Friday, it's quite easy to see why this is true. It's just that pi2, the second part of the homotopy algebra, pi2 is equal to hom, let's say isomorphic. It's the dual of the conormal module. So this is where the conormal module comes in. The idea of the proof then is we're going to show if this has finite projective dimension, then we'll take an element in here, think of it as something in pi2, and we're going to show that if I mod I squared has finite projective dimension, then that forces everything to be radical. So everything here has to be radical. If this has finite projective dimension, then all the things here have to be radical elements. So that's what we're going to do. There is a precursor to this kind of idea. So here's a theorem, Theorem of Vienga, from 2001, which says you take, I'm sort of drastically rephrasing this to fit into, to fit into this narrative, but he proved a theorem which essentially says the following thing. And let's say it corresponds to an element of pi2, and I'm going to be lazy, and I'm just going to kind of identify these and think of this just the same. So if I have an element dual functional on the conormal module, I'm going to think of it as an element of pi2. If U factors as I mod I squared going via S going to K, like this. So if we can factor it through a free S module, then U is central. Okay, so maybe as a remark, Yeah, so as a note, the way this was phrased was free summons of I mod I squared imply central elements give rise to central elements of the homotopy algebra. And if you stare at this for a while, you realize, okay, if I have this map to K and I can factor it through S, then this map here has to split. And in fact, so this becomes a free sum end of this. So if I'm in this situation ever, then I actually have a free sum end of the kernel module, and that free sum end of the kernel module is corresponding to a central element of the homotopy algebra. So Sri's motivation for this was, at least his stated motivation was that he wanted to construct central elements of the homotopy algebra to test a conjecture of Avramov, because Avramov has a conjecture, which is still wide open, saying that every single central element of the homotopy algebra should come from a deformation in some sense. So I can't properly explain what that means, but he's saying that central elements should actually have some conceptual explanation for why they're there. So there's that. And I will write down another theorem, which says the following thing. This is kind of the key result, which goes into proving the Vasconcelos conjecture, and this is the result which I'll sketch how to prove next time. Maybe once again, I don't know if people are complaining in the chat, but they should. This again, the projective dimension of the homomorphism should always be finite. So here as well, the projective dimension of phi for this result has to be finite. If we take an element here, once again, something dual to the kernel module, and it corresponds to an element of pi 2, which I'll just once again slightly abuse notation and call pi. I'll say it's just the same element, u and pi 2 of r. And if u factors as I mod I squared to m to k, where instead of now having s here, I'm just going to put something of finite projective dimension. So rather than putting a free module, rather than saying u has to go through a free module, I'm saying it has to go through a module of finite projective dimension. So with say m is finitely generated S module of finite projective dimension. In that case, U is radical. So let's get another box. Not the best box. Okay, so I tried to put this in a way that looks similar to Sri's result. So what Sri does is give a criterion for when an element of the homotopy algebra is central. And this one kind of upgrades that to being a condition for when an element is radical in the homotopy algebra. It's very similar. Instead of factoring for a free module, it just factors through some module as finite projective dimension. Okay, so the idea here is maybe even now I can sketch proof of Vasconcelos' conjecture. If I assume this, so let's assume this theorem. So we should, what Vasconcelos' conjecture says is that if we assume that the projective dimension of the kernel module is finite, then what I'm going to do in this result is take m to be equal to I mod I squared, because if I mod I squared itself has finite projective dimension, then I can always just use this. So we take m equals I mod I squared in the theorem, and then, of course, every map out of I mod I squared factors through I mod I squared. So according to this theorem, every U is radical. And then by Avramov and Halperin's result, phi is a complete section. Okay, so I hope this argument makes sense, because this is like kind of the core thing. That's how we get at being a complete section. So the key result is to prove this theorem here, that this criterion for when you have radical elements in the homotopy algebra. So that's the goal for next time. I will explain in detail how to construct this by using DG algebras, and then once we have that construction, we analyze it a bit more closely, and I'll explain why this theorem is true. So what did I have next to say? So anyway, the goal for the next talk it will start with DG algebras, and then it will go definition of the homotopy algebra, and then it will be the proof of this theorem here. This one about telling whether something is radical or not. I'm worried about I'm moving too much. So how am I doing for time, by the way? Should I stop?
Yeah, time is almost over.
Okay.
Yeah.
So I didn't get onto starting the proofs, but this is a good time to, this is actually a good point to stop, to be honest. So maybe I can do questions at this point.
Yeah. Okay. Yeah, so are there any questions? Yeah, Sarang is asking a question, is there a way of detecting set theoretic complete intersections?
That's a really good question. I've actually not thought about that question before. So one thing to worry about is that in this, if I go all the way back to, if I go all the way back to this theorem, if I have a set theoretic complete intersection which is not itself a complete intersection, then unfortunately we're in this case. So we have a very complicated homotopy algebra which is growing exponentially. So we are in a situation where we have a really complicated homotopy algebra. So there's not going to be anything like very simple that we can see inside it to tell us whether we have a set theoretic complete intersection. But it's still possible that maybe some modification of the homotopy algebra to like maybe systematically ignoring nilpotence or something. That's an interesting question. I just don't know, but I would say it's possible. I mean, my problem for answering that is I don't know much about those. I don't know about homological criteria for set theoretic complete intersections which exist, which might be used to build on.
Yeah, how does the projective dimension change if you replace I by its radical?
Yeah, that's exactly the question. That might be related to this question of Eisenbud and Mazur about the replacing I mod I squared by I mod the symbolic power of I. This would be a similar thing, which is also a difficult problem.
Yeah. So one can ask similar questions for I to the n over I to the n plus 1.
Oh, yeah. Oh, that's very interesting. So these would correspond to these methods will not apply directly to that because these are in some sense that's worth thinking about because I to the n mod I to the n plus 1. So one way to think about what's going on here is there's a connection between the cotangent complex and I mod I squared. And I to the n mod I to the n plus 1 is connected to something called the higher cotangent complex, which is like something showing up in the Hodge decomposition, which is a thing. And now that I think about it, it's very plausible that you could have similar results connecting the higher cotangent complex to these higher conormal modules, I to the n mod I to the n plus 1. So similar methods might actually apply to that.
Mhm.
I haven't thought about it though. That's quite interesting.
Yeah. Any other questions? Okay. See any further question, Ben? So we will meet next time at the same time, 7 o'clock Mumbai time.
Okay.